right? In this electron transport chain, we need oxygen. So how fast your oxygen is actually coming in, grabbing those electrons, being converted to water, and your synthase is making lots of ATP, that is your metabolic rate. That is how fast. How fast am I taking in oxygen, burning that oxygen, and ultimately making ATP? This is metabolism. We're just doing all that, that's metabolism. That's the core pathways of metabolism, okay? So how much oxygen you can take in really gives us information about what is your metabolic rate, right? How fast are you taking in and burning oxygen? This will actually increase, of course, if you move. With physical activity, doing more exercises, you need more oxygen, needs to get to the tissues, the blood, the muscles, all that stuff. That's going to increase that level, okay? So it's increased by exercise and eating, believe it or not. The more you exercise or physically exert yourself, and the more you eat, you will actually increase, ramp up your metabolism. Why? Because oxygen is needed to power this process. Food is needed to power this process. So all you really have to do is up activity levels, even a little bit, eat more, your metabolic rate goes up, right? Because I need to sustain all the cells and tissues in my body, and we are aerobic respiration organisms. We need oxygen. So that's the core of what we need. Body temperature is also an important factor in your metabolic rate. So everybody's metabolic rate, we have standards and norms, but it's very unique. It's each individual we can measure. It's not like there's just one straight number and we're all right there. It depends on all these different things. How much you physically exert yourself, how much you eat. What is your overall body temperature? Body temperature, remember, we've already talked about, increases reaction rates. This speeds up enzymes and the ability of enzymes to convert one substrate into a product, how fast they can work. All of this is built on enzymes. All these different pathways. There's enzymes that have all kinds of crazy names, and they're all part of those pathways. So a warm body temperature speeds up reaction rate. It speeds up enzymes. It speeds up enzymes that are catalyzing all of these aerobic respiration pathways. You've got a control area in your brain, the hypothalamus. It helps to correct and fix deviations from your body temperature. So when you exercise, you get real warm, you heat up. Your brain helps you go, okay, we need to cool back down again. It's cold outside, you need to get warm. What happens when it's cold outside? You walk outside and you don't have a sweater.
Start shivering.
You shiver. Your brain goes, we need muscles to contract, we need to generate heat, we need to shiver. Okay, so your thermogenesis basically, or increasing body temperature. Body responses to keep your body temperature warm. Your basal metabolic rate, we will call this BMR. Basal metabolic rate, that is the oxygen consumed by a relaxed, awake person 12 to 14 hours after eating. Okay, so you're not moving, not excited, you haven't eaten lately, because if you've eaten lately, it'll increase it a little bit because of the effects of food and exercise on metabolism. So usually it's the next morning after fasting, after sleeping, in a nice room temperature environment, calm, just breathing into a tube, and we measure how much oxygen you're consuming per minute. Notice this is affected by sex or gender, age, and your body surface area. We're going to measure that in lab tomorrow, your body surface area. So we can all start getting ideas about, okay, what is my basal metabolic rate? Like based on my gender, my age, and the surface area of my entire body, my body composition. Also thyroid activity. Your thyroid gland is right here, and it makes thyroid hormones, T3 and T4. That helps to feed into setting these reaction rates and what is your basal metabolic rate. We're going to learn the thyroid hormones later. We're not going to worry about that now. It's just one little factor that affects this process. Age, sex, and body surface area are the big factors that really help to set basal metabolic rate, or BMR. We're going to calculate that in lab. So energy metabolism, you have all of these energy reserves in your bodies so that you can use them. These are molecules you can use for energy. This is why we need to eat. Okay, we have to eat and we have to store some of that energy so we have it when we need it. Glycogen and fat are excellent sources of energy reserves. Right, we talked about glycogen. You have a lot of glycogen in the liver. You have a lot of glycogen in your muscle cells. That is branched chains of glucose that animals use to store. Right, so everything you eat, it doesn't get burned immediately. A lot of things we store it. We go, okay, we have enough right now. Let's hang on to some. So liver and skeletal muscles store a lot of glycogen. You also have fat. Where is fat stored? We have triglycerides, fatty acids. that are packed together, and we store them in certain places of our body. Where do we store them? Fat. Where's fat stored? Everywhere. But around the internal organs, that's right, around the internal organs, around the heart, the viscera, the guts, the back of the eyeball, underneath the layer of the skin, so throughout your whole covering of your body. Beneath the epidermis and the dermis, you have a layer of fat. It's called the hypodermis, or the subcutaneous region, the subskin region. That's where we store fat. So we've got sugar and fat stored in liver, muscles, and then in fat all throughout the body. Those are great sources of energy reserves. We really only use proteins in emergencies, okay? So when you consume proteins, you break them down into the amino acids, and we funnel those right into aerobic respiration. We use them coming from the diet. We also use the amino acids from proteins to build new big proteins in the body, like the fibers that are inside of your muscle cells to make your muscles stronger, bigger, thicker. We use those to build that up. Body proteins, though, like in your muscles, are really only used in emergencies. So dietary protein you break down, you use, you package, you use that to build some of the other building blocks of your body and your muscles. So we don't really use dietary proteins in emergencies, especially if you're not getting enough in your diet. You will eventually start breaking down muscle, the protein fibers and the proteins that are in skeletal muscles. So first your body will use your glycogen and fat stores, and then if those start getting depleted, your body will go, okay, we gotta start attacking the protein. Protein is the structure of your body. It makes up all the parts, the collagen fibers, the muscle fibers within them, the connective tissues, your bone. You really don't wanna start wearing away and eating away the protein, the structural proteins of your body. So this is first, second, third. That's sort of when your body needs fuel that you have stored as reserves. That's the way it goes. Molecules for energy also, of course, come from food. Just eating a big mushroom salad makes me hungry. It comes from the food that you eat, right? So you can get immediate energy by the nutrition in the foods that you take in. And you can put those through all these pathways, glycolysis, Krebs cycle, ETS. So in your bloodstream, floating around at any given moment, you have fatty acids or triglycerides when they're complex with the set of 3 fatty acids. You measured triglyceride levels in lab, right? So we did HDL, LDL, and triglyceride levels. Those are in your blood. You also have glucose floating around in your blood. You have levels of glucose that need to be maintained at a pretty constant range. So you always have circulating sugar levels. If your glucose levels start to really drop with extreme fasting and not eating, your body will start creating glucose and releasing glucose from other sources, specifically from glycogen in your liver. Okay, so you always have these free circulating glucose and fatty acid molecules. You also have amino acids that are circulating, so from your diet and consuming protein and plant and animal matter, you have those, and so those are circulating in your bloodstream. Those are carrying around the molecules that allow your body to do metabolism, break those down and convert them into ATP. Okay. This is not healthy. This is a Fanta. This is my daughter's favorite drink when we go to Mexico. We don't usually get it here. We've got these orange Tropicana and Fanta drinks. They're just so yummy. They're bad. They're loaded with 200 milligrams of sugar. They're just insanely bad, but super tasty. So that's not an example of what to eat. She was just very happy, so she got to pack a little orange Mexican tropical drink. Oops, energy. Okay, energy to form ATP comes from carbohydrates, fats, proteins we eat, or from catabolism of our body tissues. So we got to either take those molecules in and break them down, or we have to get those from the stored locations in our body. And so it says, or from catabolism of our body tissues. What does catabolism mean? Or catabolic pathways. This is something I may have mentioned briefly, but we didn't spend a lot of time on. That we have 2 types of pathways. We have catabolic pathways when we talk about nutrition and health and all this stuff, and we have anabolic pathways. Very quite simply, catabolic or catabolism pathways mean to break down. Basically, all the polymers and the monomers that you guys learned about, this is breaking down those polymers into the monomers. Anabolic pathways is actually building up, making polymers from the monomers. So these two are reciprocal, inverse reciprocals of each other. Catabolic pathways break down. This is an example of a catabolic pathway. I have sugar in my system, I have carbohydrates, I break down my glycogen, I have free glucose. Now I can break down glucose further, ultimately get ATP. That's catabolic pathways. I'm generating energy from breaking down a fuel source. Anabolic means I'm going to build up. I'm going to use the amino acids, I'm going to build them together, and I'm going to create new protein in my limbs or my muscles or my connective tissues. I think of anabolic steroids. Are you guys familiar with anabolic steroids? They're used in different ways. They're a type of androgen or testosterone that you take exogenously or inject into the blood, and it causes the building up and buffing up of the body and the muscles. Building up. Breaking down, building up. So when you use, we're getting the fuel either from what you eat or from your body breaking down its storage tissues of glycogen and fat and protein. All right. So how do we measure the energy value in food? It's measured in kilocalories. 1 kilocalorie is equal to 1 calorie, big C, which is equal to 1,000 calories, little c. Those are different, okay? And we work with kilocalories so we don't have thousands and hundreds of thousands of units to work with. We just keep it 1 kilo. Kilo means 1,000. 1 kilocalorie is 1 big C calorie, which is equal to 1,000 small c calories. So these are just units of conversion. 1 calorie is the amount of energy needed to raise 1 gram of water by 1 degree Celsius. We talked about this at the beginning with the properties of water having a very high heat capacity, a lot of energy to heat it up. So we use that to measure that. That's just what 1 little c calorie stands for. Well, what does this mean for all of you guys? What's the important part? 1 gram, which is just a little smidgen on a scale, 1 little gram of carbohydrate or protein is equal to 4 kilocalories or 4,000 little c calories, okay? That's the amount of calories, energy in ATP, basically equivalent to what you can get from a gram of that particular fuel. 1 gram of fat, the same weight of fat, provides 9 kilocalories, or 9,000 little calories, okay? So in other words, which one is a higher energy fuel source? The fat. You get twice as much bang for your buck. Matter of fact, you get 2.25 times the amount of energy measured in kilocalories, which ultimately provides us ATP to do all the work of the body, than carbohydrates or protein. But the energy requirements are different, and they depend on gender, and they depend on physical activity. So if you are super active and you move a lot, you're going to need more kilocalories a day. You're going to need 2,000, 3,000, 4,000, even 5,000, depending on what you do and how much energy you actually burn, how much you exert in all of these metabolic pathways. The average is about 1,300 to 5,000. The average person, adult male, is about 2,900 kilocalories a day. The average female is about 2,100 kilocalories a day. Excess calorie intake, regardless of the source, it doesn't matter if you're eating carbs, proteins, fats, it doesn't matter. If you take in excess calorie, then you're actually burning and using for all of these metabolic pathways and to do all the work that you do, that your body does. You will have something called a positive energy balance. That means a surplus. You've got more calories than you're even burning. If you have more calories coming in than you're actually burning and using, what will happen? You'll gain weight, right? You'll start to store. You'll go, oh, okay, I got excess. Let's hold on to it. Deposit it, store it as triglycerides, store it as the fat. You'll actually gain weight. You'll hold on to that positive energy balance. But if you consume fewer calories than you're actually needed or than you actually burn with physical activity and basal metabolic rate and the status of your body, you will have a negative energy balance and you will actually lose weight because you will start tapping into those stored fuels. So really it's just a homeostasis equilibrium of calorie intake to calorie output. Pure and simple because you're burning these things, and if you have extra, your body will store them. If your input matches your output, you'll stay exactly where you are. You won't really move anywhere. The body can adjust metabolic requirements, so this is what makes weight gain or loss and tapping into those fat stores extremely difficult. Because your body and your brain can adjust your metabolic requirements, going, oh, we're not getting a lot right now. Slow down, we're not getting a lot. Remember I said eating and exercising speed metabolism? If you're not getting enough food, your body goes, whew, we're kind of in starvation mode. Slow down. Slow down. All these metabolic pathways, slow them down. We can't waste. We gotta hold on to precious resources. Because of that, it makes that shift on that teeter-totter very difficult. You can't just go, I'm just not gonna eat, and I'm just gonna physically exert myself. That's easy, I'll just lose weight. Temporarily you can do that, but your brain will actually go, wait a second, let me slow down here, or let me speed up here. And your hypothalamus in your brain is sort of one of the bosses of sort of mediating that process, like how much is coming in versus how much is going out. Calorie expenditures, there's 3 parts. BMR, we've already talked about, basal metabolic rate. This is the amount of energy needed to maintain your body functions at rest. Basal metabolic rate, just chilling and doing nothing. How much oxygen are you burning and creating ATP from that process, just doing nothing? It's measured at rest at 28 degrees Celsius, that's room temperature. That's like here, it's like 70, 75 degrees, okay? And it's 12 hours after eating, we measure how much O2 you're consuming per minute. This roughly is 60% of your caloric burning or expenditure. That means just doing you and chilling and doing nothing, 60% of your caloric expenditure comes from BMR. The other about 10% comes from thermogenesis, adaptive thermogenesis. This is the energy needed, extended to adapt to changes in temperature and changes in eating, okay? Eating, consuming, absorbing, chewing, breaking down, getting them into the blood, that's all burning, that's all taking oxygen, that's all taking energy, right? Staying warm or cooling off, that takes energy. So balancing your body regulation, thermoregulation, with eating, we call adaptive thermogenesis, and that's about 10% of your overall calorie expenditure. The third component, and this is really one of the most important, is physical activity. BMR is 60% of what you burn, 10% is thermogenesis of what you're burning, and physical activity, this is really variable depending on activity levels, so it's about 30% or a third of your caloric expenditure, but can be even higher if you're very physically active, or even lower if you're not physically active or you're very sedentary. Just a little side note, BMR, your overall just at rest metabolic pathways, go down about 2% per year after the age of 30. This doesn't affect all of you, this affects me. And as you get older, this will affect you. So if you stay at this range, and you exercise about the same amount, your thermogenesis, staying warm, staying cool, eating, it stays about the same amount, this goes down. Overall, you end up gaining about a pound a year at the age of about 30, because these 3 are no longer matched now, this one starts to get lower. So with age, our enzymes and our metabolism, it just starts to slow down a little bit just to run the basic operational machinery, okay? So this is just a little kind of side note for as we age, sort of what happens. I'll just end right there. Are we at time? Yes, we're time. Homeostasis, energy expenditure, the energy intake, so it's like a teeter-totter, basically. It's balancing those things together. And this is actually what you're working on in your nutrition logs and physical activity journals. This exact process is what you're working on. I have office hours today if anybody wants to come by for office hours, and I will see the rest of you in lab tomorrow. Take a minute to jot something down in your card or do it an hour later.
Today, or is it
What
Friday
you got,
too?
what you didn't get, what'd you say, Jessica?
I said it's office hours just today or Friday too?
See, I have them Friday too.
Okay.